So I was asked to give a status report for inflation after Planck. I was also asked to be provocative, so I'm going to apologize ahead of time for anyone I offend. But I thought it would be, my honor to KIPAC at 10 to at least do what they asked. Okay, so first I'm going to talk about the motivations for inflation. Then I'll talk about inflation and some quote-unquote alternatives. Then I will discuss possible alternatives without quotes. And then I'll talk about what big questions are left after Planck. Okay, so the motivations for inflation. We all know the CMB is extremely uniform. We've measured the temperature to this incredible precision. And so far, it's consistent with a black body. We saw the dipole first a long time ago. It's consistent with it's a 1 part in 1,000 fluctuation of the temperature that's consistent with a relative velocity of 370 kilometers per second of us relative to the CMB. And then we've now mapped the primordial fluctuations that give us the higher multiples to incredible precision. So that was Kobe, this is WMAP, and now Planck. So the horizon problem, which I'll take as the main motivation for inflation, in 1980, we would have described just by this incredible uniformity. We would have said something about how at the surface of last scattering, the distance that light had traveled only covered some small fraction of the CMB. So when we looked in different directions in the CMB, each one of them could have only been in causal contact with some small region. So the incredible correlation in temperature between these different regions wasn't compatible with causality. But today we have an even sharper statement. We've now measured the fluctuations incredibly precisely. And when we look at small scales, what describes the temperature fluctuations are sound waves. So if this was produced by some causal mechanism before the CMB, it would have been a bunch of sines and cosines. But this incredible acoustic structure tells us that these things are all adding in phase. So that somehow this coefficient C1 of the sine part is missing, that every wave came with the exact same phase. This is explained if the modes started their life outside the horizon. So modes on superhorizon scales look like constants so that, say, the coefficient C2 is the only thing that's there, and this coefficient C1 gets driven to 0, like a cubic power of the scale factor. So the fact that all the modes are in phase are consistent with it suggests very strongly that the fluctuations had to have already been present when they were outside the horizon. This is also further supported by the TE correlation, but I won't talk about that. So why is this a problem? So if we look at what it means to be inside or outside the horizon, this co-moving k is a constant, so the question is, what happens to this a times h as a function of time? And so as a function of time, we can see that this is really just a double dot. So in a cosmology that didn't accelerate in the past, then that tells us that modes only come inside the horizon in the future. So if the modes were outside the horizon in the past, then in a non-accelerating cosmology, they were always outside the horizon. And this doesn't allow for a causal mechanism that would have required that the modes were all inside the horizon at some point when they were generated. Okay, so now how inflation solves this problem. So inflation solves this problem by just adding acceleration in the past, but further with this definition that I'll stick to. So inflation I'll define is just that we had a period of near de Sitter expansion. So near de Sitter meaning that h squared was much greater than the absolute value of h dot for some period in the past. And this solves the horizon problem for this reason that there was acceleration in the past. And to see why this works, the horizon is, when h is nearly a constant, is just some fixed size. But suppose we had some things that were in causal contact, but they get separated by the exponential growth of physical distances. So things where were in causal contacts get stretched outside the horizon exponentially in time. Now, the key that would have been true even for just pure de Sitter, which would have also had a constant h. But in practice, we also know that the universe eventually reheated, and it has, it looks like a matter-filled universe at some point. So this phase must have ended somehow and converted back into matter and radiation. So the way that this gets done is through some kind of physical clock. The standard choice is usually some scalar field where the physical clock is the rolling of the scalar field. Different moments in time are labeled by where this inflaton phi is on this potential, and then inflation ends at some critical value of phi. But really, the mechanism is true of any physical clock. This scalar field is just one particular example. Now, like any physical clock, this clock isn't perfect. There are fluctuations of the clock. So for the scalar field, we characterize those by the fluctuations of the scalar field. The fluctuations in time are characterized by fluctuations of the scalar field over phi dot. And this means that when inflation ends, the amount of inflation at different points varies due to the fluctuations of the clock. It can't measure exactly when inflation should end. So the amount of inflation varies like h times this variation in the time. And this looks like you can think of as a scalar metric perturbation. The scalar metric perturbation is just characterizing the different number of e-folds from point to point. Inflation also predicts fluctuations of the metric directly, and those are tensor modes or gravity waves. In addition, we can read off what the scale dependence of the power spectrum is. Roughly speaking, in a de Sitter-like expansion, the fluctuations at horizon crossing are sort of the amplitude of h at that time. So horizon crossing would be defined by when k over a is equal to h. So if h was a constant, this amplitude would also be a constant, and that would mean that the spectrum was scale invariant. Inflation, by definition, is almost de Sitter, so it's almost scale invariant. And so the difference, characterized by ns minus 1, is given by the time derivatives h over h or h dot. And by this definition of h dot much less than h squared and h double dot much less than h dot h, this number is much less than 1. And this is basically just what I mean by inflation. So what are some alternatives to this picture? Well, if all I ask is that there's accelerated expansion, I could have done this with any geometry that has a double dot greater than 0. So h could have evolved with time in a much more dramatic way, just so long as that a double dot is greater than 0. And this is true for any, say, perfect fluid with w less than minus a third. You could also do this a different way, which is to just patch into the past a time reflection of a normal cosmology. So you have a collapsing cosmology in the past, which you then need a bounce to continue to expansion in the future. And in this case, what happens is that the modes go outside the horizon only because the horizon is shrinking faster than the separation between points. So this is just a time reflection of what happens in sort of ordinary matter-dominated universe. But of course, this getting a bounce is a very non-trivial feature that I won't talk about, but is definitely a major obstacle to writing down a real model. Unfortunately, scale invariance is lost in these models. So by the exact same logic that inflation predicts scale invariance because h is constant, if I get rid of the constancy of h, then I will typically expect to lose, I'll expect to lose scale invariance. And it's been shown that you basically can't make this work with just the fluctuations of the energy density that drives inflation. Now there's a cheap fix to this, which instead of trying to use the clock to generate the perturbations, you add an extra degree of freedom. The easiest way to do this is actually just to make this extra degree of freedom think it lives in de Sitter space so that its solutions look the same as a scalar field that lives in de Sitter. This has a characteristic feature that the gravity waves won't actually see a real de Sitter metric, so they will not be scale invariant. So what are the predictions of the inflation versus alternatives? Well, inflation predicts near scale invariant power spectrum, and it predicts nearly scale invariant gravity waves. These alternatives can accommodate scale invariance, but we have to work hard to do it, and they can't even accommodate scale invariant gravity waves. But neither one predicts any particular level of non-Gaussianity in a model-independent sense. So what's the results from Planck? Well, as has been emphasized previously, we have this amazing measurement of ns different than 1, but different just at the 4% level. We have yet to see gravity waves, but we're pushing that down. But this also is a plot that many people have seen that shows the mutual constraint on ns and the tensors. Okay, so I kept using searches for alternatives in quotes. So I kept saying that because I don't really think that these are true alternatives. They don't solve, so why do I say that? All of these examples solve the horizon problem in exactly the same way. They extend the geometry to the past, and then they generate fluctuations from quantum mechanical fluctuations that then evolve outside the horizon. So both are basically doing the exact same thing. Inflation just works better. So this is my personal opinion. There are some fine-tuning arguments that happen about whether this inflation works better holds up, but I personally don't know if these can be quantified in a way that everyone would agree. So at the level of predictions, I think inflation just explains the data better. On the other hand, since these alternatives are so similar, you might ask, has the data really already ruled out anything more exotic? Do we all agree that the data requires that we extend the geometry to the past, and that that's the only way to do it, and that we're just discussing details as to whether it looks like de Sitter or something slightly not like de Sitter or some collapsing geometry? So the solution that doesn't exist yet is to say that there's always a singularity in the past in cosmology. We need quantum gravity to complete this singularity, to tell us what happens when the densities get high. And maybe the answer is just that there's some magic from quantum gravity that explains why the initial conditions just happen to be scale invariant, or nearly scale invariant over these scales. So this is often, I've heard this stated in the following way. Scale invariance or near scale invariance is ubiquitous in physics. Why can't the reason that the fluctuations have the origin just be similar to the examples we know in physics? There's no deep mystery. It's just, just like all other physical systems that have scale invariance. So let's ask if at least that sentiment is plausible. So what's true in all the examples we know of where scale invariant or near scale invariance appears in physics, what we have is the following. Well, often it has the following structure. We have a Gaussian scale invariant theory, and then there's a nonlinear term controlled by some parameter I'll call lambda. This parameter controls the size of non-Gaussianity because it's controlling some nonlinearity that's strictly non-Gaussian. Now, when you compute corrections due to this nonlinearity, at some order, let's say at order lambda squared, you find that the scale invariance of this theory is broken due to the corrections due to nonlinearity. So in all these examples, what you find is that these theories are strictly more non-Gaussian than they are not scale invariant. So what does Planck have to say about this? Well, so I'll brush over what they actually do because Kendrick just did a nice job explaining it. The main takeaway is that the sort of measure of overall non-Gaussianity is this FNL parameter times the size of the square root of the power spectrum. So sort of FNL times 10 to the minus 5 is sort of the overall non-Gaussianness you should have in mind. So as Kendrick showed, there's some parameters on different shapes. There's sort of FNL of order 10 or order 100 that have been constrained by data. So this is the three different shapes he's talked about. So using these constraints, you find that the amount of non-Gaussianity in the data is less than about 1 part in 1,000. On the other hand, we've now detected scale invariance at 4%. So the data is most definitely more Gaussian than scale invariant. And this is not like what we see in physics. So in other examples of physics, like QED or phase transitions, it's strictly true. It's true in those examples that the theories are simply more non-Gaussian than they are not scale invariant. So I don't take this as, this could never rule out my second solution, since I don't even have a working model. But I think this is actually an example of something interesting that happens in inflation that's not just this, oh, scale invariance is ubiquitous, why does it have to be inflation? So what are the open questions? What would we like to see in the future? So as may have been clear so far, the question of was it inflation, I think the evidence is pretty compelling. Now, people who still really like these collapsing geometries, I think, or alternatives, I think really think a detection of scale invariant gravity waves would probably admit really kills those alternatives. And the search is ongoing through these B-mode experiments. Now, what this would do was still provide this, a detection of scale invariant gravity waves would really give a great confirmation of this inequality, that h squared is much greater than h dot, which was really our definition of inflation. Now, this doesn't test my radical alternative, some quantum gravity, because in this example that I don't have, maybe gravity waves also come out scale invariant. So if we really want to consider alternatives that don't look like inflation, then we really need some new ideas, because it's hard to know what to compare to since there's no real alternative. I think the more relevant question that we can really test in the future that hasn't been tested so far is really, what is this physical clock? Right now, all we've determined is that we need some type of clock to end inflation. And what we've tested so far is how good this clock is. So what we've sort of estimated is the error in the measurement of time over the dynamical time of our clock, sort of accurate at 1 part in 10 to the 5. Now, we make clocks like this on Earth all the time. We can actually make clocks more accurate than this, and we don't require a scalar field to do it. You know, we take cold atoms and we do stuff with them. So is it really true that to explain data we need a fundamental scalar field, when in reality all we're really testing is the existence of a clock? So what might you expect from some alternative, something that didn't require a fundamental scalar field? My guess is that it requires non-Gaussianity. The reason is that if you take something that's not made of a fundamental scalar, you still want to make this thing called time that's basically a scalar under rotations. So if you had some particles, you had some atoms that aren't scalars, you need to glue them together so that you make a scalar. So you need some kind of force that holds whatever you're making your clock out of together, and this looks like interactions or nonlinearities. So for example, you know, we have fermions that make up the real world, but we glue them together using E and M to make atoms, which then we make our clocks out of. Now, the current limits on non-Gaussianity for this type of question, I think, are still pretty weak. Any detection of FNL equilateral greater than 0.93 would rule out single field slow roll inflation. I put the 0.93 just to prove that I actually did a calculation to determine this and didn't twiddle it. But you could put 1 there and you'd be just fine. But the Planck error bar here is 75. So we still have about 2 orders of magnitude to go before a detection of non-Gaussianity could still be consistent with single field slow roll. So that means that any detection in this range would really tell us something dramatic about what's going on in the early universe. This isn't to say that the measurements aren't interesting until you get to FNL equal 1. It tells you that they're always interesting until you get to FNL equals 1. Lastly, we might ask, was quantum gravity important to inflation? This I didn't put a lot of emphasis on because it's been covered in many talks. But one of the features of inflation that's very interesting is that it seems to be very sensitive to the Planck scale. So an example that some people mentioned was that we can tell from observation if the field range traveled more than a Planck distance. And this is important because if it traveled more than a Planck distance, it's sensitive to an infinite number of corrections of this type that go like phi to the n over m Planck. We'd be able to tell this from B modes through something called the Leith bound, that if you detect r greater than 10 to the minus 3, then it meant that the field traversed a super-Planckian distance. So this would tell us at least that Planckian physics had to play an important role in such a detection. But we might ask if there are other ways to see it. Are there other observables that would really highlight the role of Planck scale physics? These are open questions. It would be interesting to have other observables where we could cleanly distinguish some need for understanding physics at the Planck scale. Okay, so to summarize, I think inflation offers a compelling explanation of the data. I think the question of whether or not it's inflation is maybe oversold. I think the data has pretty strong evidence that we see h squared much greater than h dot in the early universe. If we want to push our understanding of this, there are two main probes. There's the search for gravity waves through B mode polarization, and there's the search for non-Gaussianity. This, as Kendrick emphasized, will probably require going to large-scale structure, which is where sort of the source of a lot of modes lies, and hopefully we can get better constraints from there. Both of them are important. I wouldn't want to prioritize either one, but I think both should be taken equally seriously. Okay, thank you.
How late could inflation end without violating existing observational constraints?
I am under the impression that without adding in details of a model of dark matter, that you just have to have a reheat temperature above, high enough for BBN. So that, that could tell you the inflationary energy scale was extremely low because you just have to be able to reheat to a few MeV. But if you start adding in more physics, like some model of baryogenesis or something like that, then you get a lot more constraints. But without any knowledge of physics beyond the standard model, the constraints on when inflation ends are very weak.
More questions?
Yeah, I wanted to, I'm sure you know this, but I think I agree with you that alternatives are in quotation marks because they're pretty embarrassing. But I think every model of multi-field, the only alternatives are multi-field, and multi-field really must have FNL local bigger than 1, of order 1. Because it's a conversion mechanism. These are fluctuations that think they live in the sitter, and then they get converted. So I think another threshold here would be really to get FNL local of order 1. Because it will roll down multi-field, and since there is a theorem, then it's inflation for sure.
I avoided commenting on multi-field because I guess it depends on what you mean by multi-field. You know that we could just add some extra scalars that are sort of around for the ride and contribute part of the perturbations. And those you can make the FNL local contribution basically whatever you want. But I think what you have in more mind is something like where all of the perturbations come from extrascalar field. And then I'm under, FNL of order 1 sounds plausible, but I don't know of a theorem that says that that's a requirement.